Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week in Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories in the news. First of all, I'd like to wish everyone a nice Thanksgiving weekend and also happy holidays. But you see, for physicists, this month is very important because it marks the 100th anniversary of the publication of one of the most influential science papers of all time, Albert Einstein's General Theory of Relativity, published in November of 1915. Why is it important? Only because it changed everything. Our understanding of the universe, its origin, the birth of the universe, the Big Bang, black holes, all of it stemming from Einstein's general theory of relativity that we are celebrating around the world this month. And also, the press calls it the Battle of the Billionaires. Two billionaire entrepreneurs are fighting to see which company they created can create the reusable rocket. We're talking about Elon Musk, the founder of SpaceX and Tesla Motors, versus Jeff Bezos, the founder of Amazon. Both of them are entrepreneurs fielding rockets that may one day carry tourists and you and me into outer space. But is it really a battle of the billionaires? And if so, who wins and who loses? Also, the whole question of solar flares is back in the news again. Several years ago, I did a major story about the possibility that the sun could suddenly erupt into a monster, gigantic solar flare that could wipe out telecommunications, power lines, cause trillions of dollars in property damage, and finally, the White House is beginning to take the threat seriously. So we'll talk about what could happen in case a monster solar flare from the sun strikes the Earth. And also, speaking about outer space, scientists have announced that they've been able to make tiny quantities of diamond nanotubes. In fact, it is the hardest substance known to science. So far, they've only been able to make quantities smaller than that of the width of a human hair. But one day carbon nanotubes could be used to create a space elevator. Can you imagine going into outer space by hitting the up button of an elevator and just like Jack and the Beanstalk climbing up the beanstalk? Well, that reality is still maybe 100 years away, but at least it's within the realm of physics. And then in the second half of Exploration, we're going to bring on our special guest today. We're going to talk about fusion. Is fusion power, the power of the sun, really a viable technology, or is it nothing but a pie in the sky? You know, the joke is that every 20 years, we physicists make the solemn announcement that 20 years from now, we will have controlled fusion. That is, energy for free. And then 20 years later, we say, oh, well, we don't quite have it yet. Give us another 20 years. But the question is, how many more 20-year predictions can the public tolerate before it finally pulls the plug on funding for a fusion machine? So we'll talk about energy, and we'll talk about fusion with NYU Professor Charles Seif. Well, let's just jump right into some of the top stories of the past week. Our top story today is that 100 years ago, Albert Einstein published a paper which changed our whole conception of the universe. Realize that back in 1915, people thought that the universe was the Milky Way galaxy. If you were to talk to an astronomer back then, and you were to ask the astronomer, how big is the universe anyway? The astronomers would most likely say, well, the universe is the Milky Way galaxy, and the Milky Way galaxy was perhaps maybe 100,000 light years across, so there you have it. That is called the universe. Boy, were they wrong. We now realize that they were way off back in 1915 when Einstein published this paper. Einstein's paper was revolutionary because it introduced the concept that you can actually study the evolution of the entire universe. And he did that by assuming that space could be curved. Now, let me explain. It was William Shakespeare who introduced the metaphor that all the world is a stage, and we are actors and actresses making our entrances and exits on the stage of life. Well, along comes Einstein, who says, not so fast, not so fast. The stage is not flat at all. It's not like the stage of a theater. It's curved. It's curved, meaning that when actors and actresses roam across the stage, they cannot move in a straight line. Because the stage is curved, they say that there is a force that is tugging them to the left and tugging them to the right. Well, we know there's no force. It's just that the stage is warped. Well, we now think that the universe is like the stage. And the presence of matter, the presence of stars, warps space so that you cannot move in a straight line. In fact, you orbit around a star because the star curves the space around you. So in other words, objects move due to gravity, not because there's a force of gravity, but because space is curved. And so then the question is, why are you sitting in your chair today? Now, you may say to yourself, that's kind of a stupid question. Everybody knows that gravity is pulling me down to the floor, and that's why I'm sitting in my chair now. Well, Einstein says, no. Gravitational pull is a fiction. It doesn't really exist at all. The Earth is curving the space around you, and therefore it is pushing you down. So in other words, the space around you is pushing your head into the floor. So in other words, if you want to summarize relativity in one sentence, it would be that gravity does not pull. Space pushes. And because space is invisible and you can't see it, it means that gravity is like a mysterious force that pervades everything. Well, Einstein says there's no force at all. It's nothing but the curvature of space-time. Now, when he first proposed it, it was revolutionary because then you could start to make estimates about the curvature of the entire universe. So the picture emerging from Einstein is that the universe is a sphere of some sort. We live on the sphere of the bubble, and the bubble is expanding. That is called the Big Bang Theory. Because if you run the videotape backwards to the beginning of time, then the universe is quite small, and it emerged from a dot, and that is the Big Bang Theory. Now, believe it or not, we have ample experimental verification of this radical idea. In fact, we have thousands of data points measuring the radiation of the expansion, the rate of expansion, and every single point fits Einstein's theory of general relativity. Now, some people say to me, Professor, let's say I don't like relativity. Give me another idea. Well, I tell people it's a free country. You can believe anything you want. It's a free country. But if you think, for example, that the Easter Bunny created the universe, well, your Easter Bunny has to match thousands of data points. Each data point fits Einstein's theory precisely. So it's just not a theory anymore. As far as we're concerned, it's a fact that space is curved the way Einstein predicted. Perhaps one of the most graphic verifications of this is the fact that if space is curved, it will also curve light. Therefore, light from a distant star will not travel in a straight line. In fact, if a light beam from very, very far away moves past a galaxy, it will curve just as if it's a light ray going through glass. That's why your glasses work. Your glasses bend light. Even though, of course, glass is invisible, you can see your glasses because it bends light. In the same way, you can have lenses. Lenses in outer space, except these lenses are made out of galaxies. And the light moving around a distant galaxy bends just the way light bends in your glass. This means you're going to have optical illusions. Just like you can have optical illusions because your glasses bend light. And sure enough, bingo, these are called Einstein lenses and Einstein's rings. We see exactly the optical illusions predicted by Einstein's theory. Not to mention the fact that Einstein's theory also makes possible black holes, and we see these things in outer space. No longer science fiction. In fact, right in our own backyard, at the center of the Milky Way galaxy, There is a raging black hole that weighs 2 to 3 million times the mass of our sun. And if you want to see it tonight, go outside, look in the direction of Sagittarius. In Sagittarius, you'll find the galactic nuclei, the center of the galaxy itself. By rights, the galactic nuclei should be a gigantic fireball. A fireball that lights up the night sky. Unfortunately, because of dust clouds, you really can't see too much. But take my word for it, astronomers have identified a black hole at the very center of the galactic nuclei, meaning that, once again, yet another prediction of Einstein's theory has been verified. In fact, Nobel Prizes are given to physicists who work on the crumbs left from Einstein's table. Let me give you another example. If I have two dying stars called pulsars, they could be rotating around each other because they have equal mass, and it's like a dog chasing its tail. So imagine two pulsars rotating around each other like two bells in a dumbbell. Well, because space is curved and takes energy for them to wrap around, they gradually will lose energy. Newton would say, no, you can rotate around each other forever. Einstein says, no, it takes energy to bend space, and therefore it's like moving in molasses. There is a wake created by an object moving in molasses, the molasses being the fabric of space and time. So the two pulsars lose energy, and eventually they get closer and closer together until eventually they collide. Well, astronomers identified two pulsars in a double-star system. They calculated the rate at which the radius was contracting, and bingo, right on the dot. Just like Einstein's theory of general relativity predicted, it predicted the rate at which the two stars are coming close to each other. Now, in addition, if you include Einstein's 1905 theory, then you begin to realize that the foundation of modern society depends in large part on Einstein's theory of relativity. Not just the atomic bomb coming from his celebrated equation E equals mc squared, but laser beams also come from Einstein's theory of the photoelectric effect, not to mention the photonic theory, which makes possible modern electronics. And so much of electronics would not be possible without Einstein's contribution to the quantum theory and relativity. And you have another contribution right in your pocket. Take out your cell phone. Your cell phone has a GPS monitor on it, and you have to use Einstein's theory of relativity in order for the GPS system to work. You see, time beats at different rates throughout the universe. Time beats faster on the moon than it does on the Earth. Believe it or not, a clock on the moon will be slightly faster than a clock on the Earth. A clock on Jupiter will be slightly slower than a clock on the planet Earth. And because the GPS system is moving rapidly in outer space, traveling at about 18,000 miles per hour, a clock on a satellite would be slightly slower than a clock on the planet Earth. And therefore, the GPS system has to compensate for that in order for it to work. And so some people say, well, what has Einstein done for me lately? And the answer is everything. Our whole modern society with the internet and transistors and lasers and satellites, a lot of that depends upon the foundation laid by Einstein's theory of relativity and also the quantum theory. Also moving on to the next story, also concerns outer space. The press is calling it the Battle of the Billionaires. Two billionaires, Elon Musk, the founder of SpaceX and Tesla Motors and PayPal, versus Jeff Bezos, the father of Amazon. Each of them, in turn, have created rocket companies whose goal is to have a reusable rocket. Now, just remember that it was President Barack Obama who canceled the space shuttle, canceled the replacement for the space shuttle, canceled the Mars program, and canceled the moon program as well. It was a grand slam, pretty much canceling the manned space program. However, in all fairness, we should point out that President Barack Obama wanted to give a jump to the commercialization of outer space. Let commercial enterprises pay for the space program, he said, rather than the taxpayer. So we have entrepreneurs who smell a buck, and they realize that they could become billionaires many times over if they can perfect the reusable rocket. Just remember, the rockets go up, and when they come down, they splash in the ocean, and boy, we've just wasted millions of dollars of hardware. Why not have a rocket that is usable like an airplane? Well, there's a problem there. And the problem is that once the booster rocket takes you into orbit, the booster rocket is simply detached and is allowed to plunge in the ocean. For it to land vertically on a launch pad, it would have to have a very sophisticated booster rocket guidance system, as well as rockets and retro rockets to guide it back to the planet Earth. Well, Elon Musk tried several times to land the rocket from SpaceX. Each time it came very close, but it failed. We should also point out that these rockets are orbital in the sense that they're designed to shoot things into a complete orbit around the planet Earth. Well, Blue Origins is the company founded by Jeff Bezos, and it succeeded. It succeeded in actually landing its rocket. It was a suborbital rocket. It wasn't really a fully orbiting rocket, and so the velocity was less than Elon Musk's rocket, but the very fact that it did it was sensational. The press went crazy because this could be a milestone. Realize that to put a pound of anything into near-Earth orbit costs about $10,000. That's your weight in gold. Your weight in gold. And that's the reason why space travel is so expensive, because the booster rocket simply takes you into orbit and then falls away, crashing into the planet Earth. So why not have a rocket that is usable? And that's what it's all about. If we had a usable rocket, we could then begin perhaps fulfilling the dream of reducing the cost of space travel by introducing the commercial sector. And also, speaking of President Barack Obama, it turns out that the White House is finally acknowledging the fact that, yes, a gigantic solar flare poses one of the greatest threats to modern civilization. Let me explain. Back in 1859, a long time ago, there was a gigantic solar flare that erupted on the sun, seen by British astronomer Carrington. Today we call it the Carrington event. It was a humongous solar flare erupting on the sun, and the flare, like a bullet, went through space and hit the Earth. Well, back then, in 1859, we didn't have much electronics, we didn't have much of a space program, and so the damage was rather minimal. However, we scientists have tried to recreate the damage inflicted on the Earth by that solar flare, and we now realize that it would have been a catastrophe if something like that hit the Earth in modern times. First of all, telegraph wires were set afire. Telegraph wires that were shut down suddenly came alive because they were energized by the electricity generated by a solar flare 93 million miles away. Also, it turns out that the aurora borealis, the northern lights created by the solar flares, could be seen all the way as far as Cuba. Can you imagine? People said they could read the newspaper at night by the light of the solar flares, the light of the aurora borealis, as it lit up the night sky as far south as Cuba. Well, given these snippets of information, we physicists can work backwards to calculate the energy unleashed by the sun, and it is humongous. I mean, it is off scale. If we had another Carrington event, you would know it. First of all, our satellites, many of them would be wiped out, fried because of the shock wave coming from the sun, which means that weather satellites, the internet, telecommunications, Much of our communication networks would be down as a consequence of this. That's the first thing we would notice. Then it would hit power stations. Many of our power stations are simply not designed to withstand the full brunt of a gigantic solar flare. That means we could have blackouts. It also means that our astronauts were going to be in danger because they don't have that much shielding in outer space because we didn't design the space station to withstand the full shock of a monster solar flare from the sun. And so, with a blackout, it means that property damage could be enormous. You wouldn't be able to go shopping. You wouldn't be able to buy anything because all the credit cards, things are down. Wall Street would be shut down because Wall Street depends on telecommunications. And emergency crews, fire crews, they also depend on telecommunications. All the communications would be out. Now, in previous accidents that we had, the damage was local, and so emergency crews could be imported from neighboring cities. However, this would be worldwide. It would be planetary. And as a consequence, the telecommunications of the rescuers would also be affected. In other words, we would be left helpless in the wake of a gigantic solar flare hitting the sun. Now, given the fact that it's so dangerous that society itself could be flung back 100 years into the past, you'd think that people would take the threat seriously. Nope. Back in 2008, we physicists published a study published by the National Academy of Sciences, which is funded by the United States Congress, that estimated the property damage from a typical solar flare comparable to the Carrington event. The answer was $2.6 trillion. Now, that's trillion with a T, not B. That is $1,000 billion. That's $1 trillion. $2.6 trillion was the estimate of the commercial damage created by a solar flare as it hits the planet Earth. So, in other words, the devastation would be enormous. However, there are things we can do to prepare for such a catastrophic event. First, we can reinforce and create redundant systems for our power systems. Shielding, redundancies for the power systems and for satellites. So our telecommunications, our weather satellites would not go down if we had a gigantic Carrington event in outer space. The cost would be in the millions, not trillions, and it pays to be on guard. However, the United States Congress took our recommendations and did nothing. Nothing. Zero. They simply giggled. However, now the White House at least has stated that they're going to look at this and take it seriously. So we'll see what the Obama administration does about this fact. Also, news from outer space. Scientists have been able to create diamond nanotubes. Now, let me explain. We want something that is so tough, it could create miraculous devices. For example, for the space program, a space elevator. That's right, an elevator to outer space. Think about a ball on a string. Why doesn't the ball fall down? Well, it's because of centrifugal force, because you're spinning it very rapidly. Well, if I have a ball in outer space connected to the Earth by a rope, then it's like a ball on a string. Therefore, it will not fall down. It'll simply hover in outer space as if by magic. This is the space elevator. It was first theorized in 1895 that Newton's laws of motion are compatible, fully compatible, with a beanstalk to heaven. It's called the space elevator, the subject of many science fiction stories. However, if you do the math, you find some rather discouraging results. First, you find that the tension on the space elevator thread, keeping it afloat, would be so great that even a steel cable will snap. As a consequence, the idea languished for 100 years. However, now we have nanotubes, carbon nanotubes, and they are tougher than steel. In fact, they are the strongest materials known to science. And just last week, it was announced by scientists that they've created out of diamond a new form of nanotube strong enough to support a space elevator. However, we should also point out the downside of this discovery, and that is the amount. The amount of carbon nanotubes is smaller than a human hair. So in other words, it's a technical problem, but nonetheless, it is a problem to create enough carbon nanotubes to sustain a space elevator. And so in other words, carbon nanotubes are so strong, you could support a bridge with threads of carbon nanotubes. That's how strong they are. And you can make sheets out of carbon nanotube. And it turns out that these carbon sheets are also the strongest substances known to science. In fact, you can take an elephant, suspend an elephant on a pencil, and put the pencil on a sheet of carbon, and the carbon sheet will not break at all. That's the power and promise of carbon chemistry. The problem is we can only make tiny quantities of it. One day, perhaps some inventor will find a way to make large quantities of it, and then we might literally have an elevator into outer space. Now, let's be honest. We're talking about a technology that's maybe 100 years away. It's not going to happen anytime soon, but it's well within the laws of physics that one day we might be able to reduce the cost of space travel to the point that it's no more than an elevator ride into outer space. So we push the up button, and instead of going to the lingerie section, we wind up on the moon instead. Well, at least that's the vision given to us by the laws of physics and by dreamers of science fiction. We're going to talk about fusion power, not fission power. Is it possible that one day we can unlock the secret of the sun? The sun uses fusion power to generate light that lights up the universe. Nature does not prefer to use fission power. Fission power is found on the Earth, in fact, perhaps only on the planet Earth. It creates problems of meltdowns, nuclear waste, because when you split the uranium atom, you get lots of junk coming out, but not fusion. Fusion is clean. And the question is, will we one day have fusion power? Stay tuned. Welcome. Once again, this is Dr. Michio Kaku, Professor of Physics, and this is the second half of Exploration. In the first part of Exploration, we summarize some of the big stories in science, including the fact that November 2015 marks the 100th anniversary of the founding of general relativity by Albert Einstein, and that theory changed everything with regards to our understanding of the universe. In fact, much of modern society today is a direct consequence of the work of Albert Einstein. Well, in the second half of Exploration, we're now going to talk about energy. How will we find energy for the future that does not disrupt the atmosphere, triggering global warming? Well, science fiction writers for years have said the obvious choice is fusion power. But fusion power has been quite elusive. Every 20 years, we physicists solemnly say that in 20 more years, we will have fusion power, the power of the sun on the Earth. Limitless power from seawater. That's right, the hydrogen from seawater is the basic fuel for fusion reactors. Well, our best bet today is the ITER fusion reactor being built in France. The Europeans are footing the bill. It's going to cost $10 billion. $10 billion for the most advanced hot fusion reactor of its type, hoping to create energy. And again, you simply fuse the hydrogen in seawater, releasing enormous quantities of energy. We know in principle it works because that's how the sun works. The sun works by squeezing hydrogen until hydrogen fuses to create helium and enormous sums of energy. Well, what are the downsides? Well, on Earth we have fission reactors. Fission reactors built on splitting the uranium atom. is quite messy. When you split the uranium atom, you create large quantities of nuclear waste. That nuclear waste is the energy of the meltdown, and it's also very dangerous and has to be separated from the environment for millions of years. And who can promise that? Well, the sun does not use fission power. In fact, to the best of our knowledge, we might be the only civilization in this sector of the galaxy which uses fission power rather than fusion power. However, fusion power doesn't yet exist. So let's hope that the French, backing the ITER fusion reactor, can get the fusion reactor up and running so that seawater will energize the future. Once again, our special guest today is Professor Charles Seif of NYU, speaking about the prospects for fusion power. Professor Seif, you're a journalist. However, you've written about cosmology, and now you've written a new book called Sun in a Bottle, The Strange History of Fusion and the Science of Wishful Thinking. So how did you, as a journalist, get interested in things that most journalists avoid like the plague?
Well, I have to say I'm really a physics geek at heart. Back before I became a journalist, I studied physics and mathematics, and it was only fairly late in my education that I decided that I was more suited to writing than I was to actually performing scientific work. Mm-hmm. So even at the very beginning of my career, I was interested in writing about physics because that's what I loved. And so my career has been covering physics for a decade and change. And from the very beginning of the time that I was writing, among my first pieces was a large piece about fusion. And coming from the physics point of view, I thought of this wonderful thing which would solve the world's energy crises. And as a journalist approaching it, I saw that it was a little bit more complex than I had initially expected with my physics goggles on.
Okay, well, let's just jump right into your book. Your book starts out at some of the hairiest days of the Cold War. In 1945, the United States drops a fission bomb on Hiroshima and another fission bomb on Nagasaki based on uranium and plutonium. But then in the 1950s, a new race emerges, not with uranium and plutonium, but with the hydrogen bomb. So explain to us, what is the difference between the fission bombs that were dropped on Japan and the hydrogen bomb based on fusion?
Well, fission and fusion are two sides of the same coin. In some sense, every atom wants to be iron. It has iron envy. So things which are heavier than iron, like uranium and plutonium, want to split apart in the same sense that a ball wants to roll down a hill. And in the process of splitting apart, they release energy. Fusion, on the other hand, takes light elements. Light elements, in some sense, want to stick together and get heavier, getting closer to iron. It turns out that the fusion end of the reaction is more energetic per atom than fission. That is, breaking apart atoms gives you a lot of energy, but fusion, sticking them together, gives you a lot more. So at the end of the Manhattan Project, when the project ended, the United States had a bomb that used fission to power it. In its simplest form, basically all it did was take two hunks of uranium, stick them together, and wham, you get an explosion. So it was easy to do once you got uranium material to set off the reaction. Edward Teller, a physicist at the Manhattan Project, was very strongly in favor of using the other side of the coin, fusion, because he realized that it would lead to a weapon of unlimited power. And he called it the super. And the idea basically was to use an explosion, a fission explosion, to set off a fusion explosion, which was much greater. And Teller was right. The weapon that he eventually created was vastly more powerful than even what obliterated Hiroshima and Nagasaki. To give you a sense of scale, Hiroshima was about a 14 kiloton explosion, the equivalent of 14,000 tons of TNT exploding in the same place at the same time. The first full fusion test, called Ivy Mike, was 10 megatons, 10 million tons, almost 1,000 times larger than Hiroshima. It evaporated the island it was on, and that that was just the beginning. In theory, you can make a fusion bomb as large as you want. The biggest ever detonated was the Russian Tsar Bomba, which was more than 50 megatons of TNT. And after a certain point, it's pointless to get larger because you just wind up lifting a larger and larger column of atmosphere into space, so it doesn't do that much more damage. So even though it promised unlimited power, unless you wanted to destroy the Earth, it wasn't that much more effective at doing damage than a fission bomb. But at the same time, the Cold War was getting hot. The Russians had detonated their first nuclear weapon way before Americans thought they could get it, thanks in part to a spy operation that penetrated Los Alamos. So a panicked America realized, well, we have to get ahead of the Russians and keep nuclear supremacy. So they turned to Edward Teller's idea of super bomb as a way of staying ahead of the Russian nuclear weapon industry. And as we know, the Russians caught up very, very quickly, and it turned into a nuclear stalemate where each side had so many weapons in their arsenal that they could destroy the world many times over.
And I should also point out that when I was in high school, Edward Teller was actually my advisor, and he actually sort of guided my career in the early years when I was at Harvard. However, moving on now, we have the Cold War in full swing, and people are now used to the idea that there is a bomb 1,000 times more powerful than the Hiroshima and Nagasaki bomb. But other people have said, well, look at Mother Nature. Mother Nature uses fusion to light up the heavens. So now explain to us how Mother Nature uses the process of fusion, not fission, to light up the universe.
Yes, it's fusion is responsible for all life on Earth. The sun is essentially a big ball of hydrogen. It's hydrogen gas, and when it was coalescing, it was compressing itself under its own gravity. And collapsing, compressing objects get hot in general. And so you've got this ball of hydrogen that got hot and dense, hotter and denser. And eventually it got so hot and so dense that the hydrogen, moving extremely fast because of the energy of the temperature, the high temperatures involved, started slamming into each other with enough force to cause fusion reactions. So once you get a big ball of gas large enough to collapse under its own gravity and heat everything up high enough, you get a fusion reaction. And the fusion reaction is what makes the sun shine. These hydrogens get converted eventually into helium, release energy, and that energy shines out in all directions. That's what makes the stars shine. But this reaction is extraordinarily difficult to get going. You need such an enormous ball of hydrogen to kickstart that fusion reaction that it's hard to do. Even a mass of hydrogen the size of Jupiter is almost like a star. The problem is it's not large enough to get so hot that you start that fusion reaction in its belly. So Jupiter is, in essence, everything that a star has, except just that extra gravitational oomph to get it hot enough and tight enough to ignite.
And in fact, in the movie 2010, Arthur C. Clarke talks about aliens igniting Jupiter, so our solar system becomes a double star system. However, Jupiter would have to be about 10 times bigger at minimum in order to get ignition. Now, let's talk about the promise of fusion. Why has fusion hypnotized whole generations of inventors and quacks and top physicists? What is the promise of fusion? Why is there so much interest in it? Why have so many charlatans jumped into the game?
Imagine if you had a sun on your desktop, that in a little bottle you had a fusion reaction going. If you could get this, if you could have something like this, you basically have an unlimited source of energy. Hydrogen is abundant. It's the most abundant element in the universe. It's everywhere. It's in the ocean. Water is 2 atoms of hydrogen for 1 atom of oxygen. So if you were able to tap into the sun's reaction and turn hydrogen into helium and releasing energy into the process, you can turn this virtually unlimited source of fuel into energy for free. And because is clean. I mean, if you wanted to, you could release it into the atmosphere and it would float up into space. And so this promises, in theory, unlimited energy with unlimited fuel and no waste. Reality is not quite as simple as that, but that is the promise.
Okay, and for Spider-Man fans, for those people who saw Spider-Man 2, Dr. Octopus creates fusion in his laboratory in Manhattan, which is not the place to do it. But the machine looks like a little sun. It looks like actually a star. You can see sunspots and solar flares on this miniature sun. However, in real life, we don't expect to create a miniature sun like in Spider-Man 2. What will a fusion reactor really look like?
Well, there's two main areas that mainstream fusion researchers are looking at to make a real fusion reactor, and they are lasers and magnets. Lasers are a very clever way of getting the heat and pressure that you need to take a hydrogen pellet and make it collapse and start fusing. Basically, you shine laser light from all directions, and you squash a tiny pellet, and as it squashes, it compresses, and hopefully it ignites. And if you manage to get lasers that are strong and efficient enough that you create more energy out of that collapsing, fusing tiny pellet of hydrogen than you consume by getting the lasers going in the first place, then you've got a source of energy. You've got a fusion reactor. No one has gotten that far, but it is theoretically possible. Another method is using magnets. It turns out that magnetic fields affect fusing plasmas like hydrogen. And if you shape a magnetic field right, you can create a bottle with which to contain a very hot cloud of hydrogen. And so a magnetic donut shaped right and with a cloud of hydrogen you throw heat in, eventually you might get a fusing plasma. And once you get that reaction going, you just have to figure out a way of piping new hydrogen in and piping fused helium out, and you've got a source of energy going. Again, these magnetic bottles aren't working to the point where you get more energy out than you put in heating the plasma and containing it. But in theory, if our magnets improve and our knowledge improves over time, you might have a magnetic bottle that contains a miniature sun.
Okay, now, because a fusion machine would use ordinary seawater, which is limitless pretty much, as the basic energy source, and because the energy released is almost limitless, the number of charlatans and quacks that have gone into the business is quite large. So let's talk about some of the false starts and some of the dashed hopes. Beginning with Dr. Richter, but the list is long, let's talk about some of the false starts.
Yes, the goal is so lofty, the unlimited energy, that the idea of fusion has attracted quacks and hoaxers and genuine scientists who are misguided from the very beginning. In 1951, the world was absolutely stunned to headlines that Argentina, of all places, had solved our energy problems forever. There was a German expat named Ronald Richter who had convinced Juan Perón to fund a research laboratory on a secret island in the middle of the lake to get fusion reactions going in what he called a solar thermotron. And he kept the world going for about a year. People were arguing back and forth. Could he have done it? Could he not have done it? It turns out Richter was barking mad. He would get this wild look in his eyes and dump a whole bunch of gunpowder into his experiment and blow the doors off of his laboratory in gigantic explosions and rush out and write fusion on a piece of ticker tape. And yet, for many months, he kept Juan Perón's government believing that he was on his way to solving the world's energy crises, and this would be a great prestige for Argentina. Eventually, physicists in Argentina convinced Perón that something was going on that was a little fishy. They went and visited the laboratory with their own Geiger counters, and if in fact you have fusion reactions going, you should be able to detect neutron radiation coming off, and they detected nothing. So they proved that Ronald Richter was perpetrating a fraud and contemporary accounts say that he wasted between $4 million and $70 million of the Argentinian treasury in the process of pursuing his dream. And he disappeared off the world stage very rapidly, as you can imagine. But, in fact, everyone who is involved in fusion in some form winds up deceiving themselves or deceiving others about their achievements. In 1958, British scientists at a very, very prestigious lab built this machine called Zeta. Zeta was a magnetic bottle of sorts, and the scientists had convinced themselves that they had gotten fusion in a laboratory. And they cracked open beers. They announced to the world that they were on their way to solving the world's energy crises. Turns out that they were wrong, that they were not seeing fusion, that they were deceiving themselves with neutrons. They were seeing neutrons, but it wasn't from fusion that they wanted. So they had to humiliate themselves on the world stage. After all these tabloids said energy to last a lifetime, no more energy bills, the British teams had to say, well, not really.
Okay, now more recently, we had this huge fiasco concerning two chemists, Pons and Fleischmann, who grabbed world attention, covers of, I think, Newsweek magazine and the New York Times, and everyone was talking about, well, did Pons and Fleischmann create fusion in a bottle? Not hot fusion, the hot fusion of lasers and magnets, but cold fusion. So tell us a little bit about cold fusion.
Yes. In 1989, two chemists, one of whom was extremely well celebrated, made this announcement to the press that absolutely stunned the world. They claimed that where these hot fusion, this magnetic fusion, this laser fusion research has been failing for years, wasting tens of billions of dollars, these two chemists, working independently, had spent $100,000, and they had solved the problem. And what they argued was that they managed to pipe hydrogen into a chunk of metal, of palladium, which has the interesting property that soaks up hydrogen like a sponge. And the theory was that if you get enough hydrogen in there, the hydrogen will be forced so close together that they might be forced to fuse. And in doing the research on their own, they thought they saw more energy coming out of their palladium cell than was going in. So they thought they had created a device which was creating fusion energy. So as you can imagine, as soon as this was announced, it was headlines everywhere. Cover of Time, cover of Newsweek, New York Times, Wall Street Journal, everywhere was talking about this for months and months and months. It turned out that the scientists were deceiving themselves. There was a bit of fishiness. Some data was moving back and forth. It's uncertain exactly what was going on, but when the cells were reproduced in better circumstances with more sophisticated equipment, it turned out that there was no excess energy, and more importantly, there were no neutrons coming out. Turns out when you fuse heavy forms of hydrogen together, you expect neutrons to fly away, and neutrons are a sign of fusion. They were seeing no neutrons, and that made it pretty clear that nothing was actually happening.
No.
However, it took it was a huge battle for years. Physicists versus chemists became a red state versus blue state thing, where the liberal elite physicists on the East Coast were trying to tear down research from chemists at the University of Utah. So it became a huge political battle that still affects the physics community on some level.
Now, you can simply calculate, using the back of an envelope, the neutron count that would occur if they really had fusion in a bottle, and it's sufficient to kill them. So the very fact that Pons and Fleischmann are still alive means that they could not possibly have attained fusion in a bottle. But then the question is, well, what did they attain? They did get net energy coming out. That's been verified by different laboratories. Some people have gone back to the literature on palladium back in the 1800s. It turns out that a person applied for a patent for one of the first cigarette lighters. He used palladium, put it in water, and attained a net amount of energy, which he used to light a flame, and he got a patent for it, a palladium cigarette lighter, and some people think that that's what they discovered. Well, what are your thoughts? It's been several years since then. What did Pons and Fleischmann really have in their bottle that gave energy? Was it a cigarette lighter or what?
It's really hard to tell. Palladium has an extraordinarily interesting chemistry. It has been fooling researchers for years, as you've noted. That not only is there that patent, a number in the early 20th century, two researchers thought they had achieved fusion in palladium. And because they were thinking along the same lines as Pons and Fleischmann were, and they thought they detected helium inside, an excess of helium inside palladium, which would be a nice sign of fusion because you're creating helium. It turns out that they were deceiving themselves because it turns out palladium soaks up helium just as well as it soaks up hydrogen, so you have enriched helium. So if they were seeing excess energy, and it's not entirely clear from the setup of the experiment that they were, I mean, they certainly thought they were. There was some sloppiness. But it's certainly possible that they were seeing it. It would most likely be a matter of chemistry, a chemical reaction where bonds are breaking, rather than a nuclear reaction where bonds in the center of a nucleus are being formed. The nuclear bonds that change atoms into other atoms are what are changed in a fusion reaction, as opposed to the attachments between atoms, which are chemical bonds, which are being changed in a chemical reaction like burning paper or cracking water. And so whatever they were seeing almost certainly was a chemical reaction. And chemical reactions are well studied, and there's only so much you can do for solving the world's energy problems with chemical reactions. In fact, burning gasoline is an extraordinarily efficient chemical reaction that allows us to power our cars. So it's not certain that there's anything there for solving the world's energy problems unless you have a nuclear reaction of some sort. It's pretty clear that that is not what they saw.
Now, to a physicist, it was absolutely staggering that you had these two respected chemists that didn't understand anything about the quantum theory. If you bring the protons together very closely, as you mentioned, then you could attain fusion. But you have to bring them really close, 10 to the minus 13 centimeters. However, in the Pons and Fleischmann experiment, these atoms are separated by 10 to the minus 8 centimeters. And you can simply, using a back-of-an-envelope calculation, this is what we give our undergraduates. Our undergraduates can calculate that the fusion you get in a bottle is almost zero as a consequence. So for the physics community, what was absolutely staggering is the fact that chemists don't know any physics at all. Well, let's move on, because we had a story, another apparently fraudulent story that just took place a few months ago, this time at Oak Ridge National Laboratory, involving something called bubble fusion. So explain to us, what is bubble fusion, and how did the Nazis, of all people, first stumble onto this whole thing called sonoluminescence?
Yes, sonoluminescence is this really bizarre reaction, and it's only very recently been understood, where basically you take sound waves and you bombard a liquid with it, and you induce what's called cavitation. Under the right circumstances, if you hit water very hard, it actually behaves like a solid, and it can crack. And just for a tiny fraction of a second, you can cause a crack in water. And what happens when you have that crack is you create a little vacuum, and that vacuum causes water to evaporate and causes a bubble. By bombarding liquids with sound waves, you cause these bubbles, and if you time those sound waves just right, you cause those bubbles to collapse very dramatically. And it was discovered that if you do this just right, you get such a dramatic collapse that you get some sort of reaction. No one quite knows exactly what it is, even today, that causes a little flash of blue light.
Well, I'm afraid that's it for Exploration. Once again, our special guest today was Professor Charles Seif of NYU. The topic of discussion was fusion power. Is it ready for prime time? Can it give us energy that we need without exacerbating the atmosphere?